Before we begin this episode, we would like to say that in the spirit of reconciliation, that we acknowledge the traditional custodians of country throughout Australia and their connections to the land, sea and community. We pay our respects to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islander people today. Welcome back to another episode of Spaghettification. I'm the Astropunk.
And I'm Steffi Bernard. Today we have with us my friend Sonja Panjkov. Sonja is a PHD student at the University of Melbourne and the ARC Centres of Excellence for both gravitational wave discovery and all-sky astrophysics in 3 dimensions, OSGrav and Astro 3D. And she's a writer for Astrobytes. She aims to understand how stars die using supernova remnants. She focuses in particular on the high-energy emission from the supernova remnants in the Magellanic Clouds using space telescopes. And I'm really excited that she's agreed to come and talk to us today.
Hi, thanks for having me.
All right, do you want to ask the first question, Mark?
Yeah, we do. Hard-hitting questions here at Spaghettification. I tell you that.
It's all about the story.
Yeah, well, we hit you with the tough ones up front. And first off, we'd like to know, how did you get into astronomy?
Well, I didn't actually pick. I never thought I would do astronomy. It was never something that I thought I would be doing when I was a kid. I kind of just ended up here. I made a series of choices and then now I'm here. So I guess in high school, I liked science. I did English, I did maths, I did languages, I did a bit of everything. And then for my undergrad degree, I did a double degree. So I did arts and science. So I majored in English and physics, but I was very much more of a physics person, not an astrophysics person. Even at that point, I was like, no, absolutely no way. And then I did honors in nuclear physics. So I was still going down a somewhat different path. But this was when I first kind of had a slight exposure to astrophysics, because my honors thesis was nuclear physics, but we were looking for isotopes or kind of signatures of nearer supernovae in samples on Earth. It was searching for evidence of dying stars on Earth, but it wasn't really astrophysics.
That's
so
really
I knew,
cool.
Yeah. So I guess core collapse supernova was in the title of my thesis, but really I didn't know really what I was talking about. And then I guess I worked for the government for a bit and I didn't enjoy that. And then I wanted to move to Melbourne because I was done with Canberra. And then I really wanted to live, near Lygon Street in the heart of Melbourne. I wanted to work with a woman. So I reached out to my supervisor, Katie Orcatel, who studies supernovae and their remnants and everything high energy in astrophysics. And that was it. And that's how I ended up here. But it was never a decision to do astrophysics. It was lots of other decisions that kind of funneled me down this path. But very happy that I'm here now.
Yeah, awesome. Me too.
What's really interesting is that every single person we've had on, I reckon every single one of them has started out with, I didn't want to get into astrophysics when I was in high school.
Yeah.
Even Fred Watson was the same. That's not what he started out wanting to do either. And now it's just an interesting one. It's everyone says the same thing. Not what I initially thought I was going to do, but
you think it's the kind of thing that people would set out being a kid wanting to do it their whole life. But I don't know. I feel like that's not actually the experience that I hear from other people. What about you, Steffi? Did you?
Oh, no, I wanted to. I spent 40 minutes on the podcast talking about my...
Fabulous. That actually doesn't surprise me. It makes sense for you. Yeah.
Question 2. Yes, you just mentioned core collapse supernovae, which perfectly leads into this question. So you study stars that explode. Can you tell us a bit about how this happens?
Well, I study stars that explode and stars that die, but I actually study them by looking at the leftover bits, not the explosion. So that's what's called a supernova remnant. So when a star dies, there are kind of 2 main pathways. One of them is core collapse supernovae, like you just said, Steffi. And the other one is type 1a supernovae. And really, which path the star ends up going down is determined largely by how much it weighs or its mass when it's born. So we can think of low mass stars, so stars with masses of 8 times the sun or less. And so they end their lives as type 1a supernovae. They go through a whole lot of, different stellar trajectories, and then eventually they become what's known as a white dwarf, so an ultra compact star. And if that star manages to find a friend, it can explode as a type 1a supernovae. So that's kind of the one route to stellar death, and the other one is for core collapse supernovae. And so these are for big stars, high mass stars with masses more than 8 times the mass of our sun. And basically when they run out of an energy source, so material to fuse in the core, that's kind of it for them. And the core collapses because there's nothing left to sustain them, and then that results in a massive explosion that we can see, and it's ultra bright, outshine the galaxy that it's in. Is very impressive, and it's why I love to study supernovae and their remnants.
Yes, I studied cold collapse supernovae for my master's, but they were very far away, so we couldn't really see any remnants at all.
Yeah, and that's why I look in the very nearby Magellanic Clouds. Yeah.
It's good old supernova remnants. There's an area of the sky that I image a lot, actually. I don't know if Steffi's told you much, but I do astrophotography, but I do it with a mobile phone.
Wow.
I use that as my astro camera on a telescope. And an area that I target a fair bit is the large and small Magellanic Clouds. So you've done some research into supernova remnants in the Magellanic Clouds, or as my daughter calls them, the large and small magic clouds.
Well, they're pretty magic. So they're technically not clouds. They're actually nearby kind of very small, lumpy galaxies that we call dwarf irregular galaxies. So there's one that's slightly larger, that's the large Magellanic Cloud, and one that's a bit smaller, the small Magellanic Cloud. And yeah, they're kind of, when we're thinking about supernova remnants, they're kind of two of the main places that we're looking, the third one being the galaxy, the Milky Way that we live in. But the galaxy, it has some issues when we're thinking about supernova remnants and observing them. So one of those issues is that a lot of stuff is blocked by the center of the galaxy. There's a lot of emission there. At a lot of different wavelengths. So we see radio, we see visible, and all of that can kind of shroud our view. And also when we're thinking about galactic supernova remnants, it's hard to work out how far away they are. And you might think that would be easier for the closer ones, but actually working out distances within the galaxy is quite an art. And so there's really large uncertainties. And if we don't know the distance, then we have a trouble working out how big something is. Because if you think of like something that looks like a small circle sitting far away, it could also be an analogy like this. It's hard to tell the distance if you don't. It's hard to tell the size if you don't know the distance. That's my point. So yeah, we often look at in the Magellanic Clouds, and that's because we know how far away they are, and they're kind of like dinner plates, kind of moving past the galaxy, and so all of the remnants that are in them are at roughly the same distance. So we can work out how big they are, and from that we can work out lots of different things like their age or the energy of the explosion or the supernova type.
Cool. So you mentioned that there are lots of different wavelengths you can look at them. And I think when people think of supernova remnants, you're thinking of the beautiful Crab Nebula or Cas A, something like this. Are you using, visible wavelengths, or are you using different ones to get different information?
Yeah, so in my work, so I'm a high energy astrophysicist. So I mainly look at X-rays, and so I use the Chandra Space Telescope. So we're observing at very high energies. But supernova remnants are special because they emit across the entire electromagnetic spectrum. So there's radio emission, which kind of tells you about how the dying star is sweeping up its environment. So that's synchrotron radiation. We also see optical emission, so visible light. And that can be observed with telescopes on Earth. And then we also see infrared, because there's lots of dust involved in supernovae, which are one of the great dust producers in the universe. And then X-rays for the really high energy emission that I look at is useful because it tells you about what the star was made of, or what elements are present in the remnant. And that's really important for working out whether it's a high mass star or a low mass star. And so when I look at my observations, I'm looking for certain signatures. So things like iron or nickel, if we see those in our observations, it's more likely to be a type 1a supernovae. And so it came from a low mass star. Whereas if we see lighter elements like oxygen or neon, it's more likely to be a higher mass star, so a core collapse supernova.
And so just for people who might not be so familiar, so why would you need to use a space telescope to look for the X-rays?
Very good question. And I guess because we're very lucky here on Earth that we have the fabulous atmosphere and magnetic field to shield us from all of this dangerous radiation. So when I'm saying X-rays, it's really no different to the X-ray you get at a hospital, to image your bones. It is dangerous, it's radiation. And so we don't want to be exposed to it. And there's lots of radiation in space. And so, the atmosphere and magnetic field shield us from that, which is great. But the downside is if we want to look at, radiation at these wavelengths coming from, other astronomical objects, we can't see unless we go outside the atmosphere. And so, that's why we use space telescopes.
And is Chandra the best one for X-rays? Or is it the only one? I've forgotten.
So there's quite a few. So there's Chandra, which has really good high resolution observations, but then there's also XMM Newton. So that's run by Europe, and then there's New Star as well. There's quite a few of them, and then kind of the previous generation, and then there's always new generation ones coming in.
Speaking of supernova remnants, so they're a popular target for astrophotographers. One in particular, which is the Veil supernova remnant. Is that one you know much about, or has there been much study done on the Veil supernova?
There probably has, but I haven't. You put me on the spot. I know the picture. I think it's nice pink and purple images. I feel
it's beautiful in colours. Yeah, it's a lovely colour. Yeah.
I know of it. I don't know so much about it, to be honest.
So what other ones, other than the Magellanic Clouds, then do you focus your study on or your research on? Is it just the Magellanic, or is there others in particular, or?
So it's mainly the Magellanic Clouds, because there's about 70 remnants in the large Magellanic Cloud, and then about 25 to 30 in the small Magellanic Cloud. So we've got quite a nice number that we can start doing, some data analysis and, make kind of meaningful conclusions from that data. I do sometimes look at galactic remnants. So I've done things like for the galactic population, trying to estimate neutron star velocities using supernova remnant. And so basically, if we have a core collapse supernova, the core of the star, the dead core, can collapse down to become very, very dense, form either a neutron star, or if it collapses down even further, a black hole, so an ultra dense object that even light can't escape from. And so basically, when we look at some remnants, we can actually see that core of the star sitting kind of towards the center, which is very, very cool. And so in a lot of the galactic remnants, we see this cloud of dust and gas, and then we see really high energy emission from the core, which is the dead star's heart, basically. And so I've kind of thought about trying to estimate the velocity, because often when these neutron stars form, they're given some kind of kick, what we call a kick velocity. And so they kind of are pushed through space a little bit by the supernova itself. And so one way to kind of estimate that velocity is to look at your remnant, look at where the center might be, and then look at where the neutron star is compared to that center. So you've got some kind of distance offset, right? And if you have some constraint on the age of the remnant, which we can do by looking at our X-ray spectrum, we've got some amount of distance that's traveled from the center of the remnant to its current position and an age that it's roughly done that in. And so that allows us to kind of estimate the velocity. Honestly, it's not going to be the most accurate way of doing it, but for a lot of remnants, it's very difficult, or neutron stars, to work out exactly what their age is. And so if this is one way of working out the velocity, why not estimate it that way? And so you can do that for pretty much any supernova remnant that's been observed in the galaxy. Yeah, but none of those are super famous. In terms of the famous ones, I often look at Cassiopeia A. So that's, I think, around 350 years old. So, and they're a very beautiful remnant as well. And then there's Psycho's remnant as well in the galaxy. Sometimes we look at that. So that's a famous type 1A remnant that was famously observed as a supernova, a star becoming very bright in the night sky by the Danish astronomer Tycho Brahe. And then, we looked at the sky with an X-ray telescope or some kind of telescope a few hundred years later, and then they worked out it was the same thing that he saw, which is super cool.
Do you look at 1987A?
I do sometimes. So that one's in the Large Magellanic Cloud. Yeah, sometimes, like when I do population studies, we're trying to say things using all of the remnants in one of those galaxies. So sometimes I look at that. I haven't really looked at kind of observations and images. I've more studied it looking at the surrounding environment. But that's a really interesting example, because it was the closest kind of supernova we've seen in a long time. And it was super, super cool, because it was the first time they saw neutrinos coming from the supernova, which is really important. And it's super special as well, because we get to observe the transition from supernova to supernova remnant. Which is kind of a murky kind of boundary. And we're really seeing it evolution unfold like right before us.
And it sort of leads into my next question for you, which is how did supernova remnants tell us about the stars that made them? So I was wondering if supernova 1987A is useful because it is one where we sort of had images of the star beforehand and we could tell what sort of star turned into this core collapse supernova, but you don't usually have that information at all. So how do you use the remnant itself to tell a bit about which sort of star made it?
So there are a variety of ways that we can do that. The best way, without a doubt, is to look at your X-ray spectrum. We have our observation from Challenger or XMM, some kind of spectral instrument, where we see how many photons we're getting at different energies. And basically, when we do this, we can see what we call line emission that might come from certain elements, and just due to their kind of the structure of their atom and their like electrons and stuff like this, we'll see very specific energies that come from these elements. So yeah, when we're looking at them, when we look at our spectrum, if we see iron and nickel, these are elements that are produced in type 1a supernovae. And so if we see quite a lot of that, we're thinking, yeah, it was probably a low mass star that died as a type 1a supernova. Whereas if we see what we call alpha process elements that are formed via the alpha process in stars, so magnesium, silicon, neon, then we think core collapse. So that's without a doubt the best way to kind of type your supernova. But there are some other ways. So one thing that I work on a lot is to look at morphology, so the shape of supernova remnants. And this can kind of inform us about the supernova type. There are studies that have shown that core collapse supernovae, so big stars that die, tend to be more asymmetric. And so basically, if we look at a remnant and it's very lumpy, it's kind of elliptical or elongated, it's likely to have come from a massive star. Whereas if it's very circular, very uniform, like Tycho's supernova remnant in the galaxy, it's more likely to have come from a lower mass star. And then I guess another way, if we have absolutely no information, we haven't got good observations, stuff like this, what we can do is we can kind of think about the surrounding environment. So big stars tend to be formed in environments with other big stars. There's usually molecular clouds around. There might be lots of other stars, stuff like this. So if we're seeing a remnant in an environment like that, it's possible that it was a massive star. If we had to guess, that's what we'd pick, but it's a guess at that stage.
I'm going to push it in a slightly different direction and then come back to the next question. We've spoken a lot about supernova remnants and stars going supernova, but is there any research that you know of that, or that you've been involved with, or used the papers for your research for stars that have the potential to be going supernova in our lifetime?
So I guess the most famous one would be Betelgeuse. Everyone's always talking about Betelgeuse. I get asked this a lot. So I guess Betelgeuse is a very nearby star. It's a massive star. When we think about stars dying, sometimes there might be evidence that this is about to occur. So maybe they become very bright all of a sudden and then they fade. Maybe they become dimmer, because as stars die, there is often mass loss that's occurring. So they might be shedding some of their outer layers. There might be dust that they're ejecting, and that might shroud your star from our telescopes, making it look dimmer. And so Betelgeuse quite famously goes through periods of brightening and dimming again, and everyone always gets very excited. Yeah, I guess we can never know for sure exactly when it's going to happen. Not until it happens, and then we'll get some neutrinos, and then as soon as we see the neutrinos, everyone all of a sudden will turn their telescopes to look, because we actually see the neutrinos before we see any light, and that's because they're able to escape out of the star much faster than the light, which kind of has to work its way through. Betelgeuse is the one, and I think the most recent paper I said was perhaps in the next few centuries, but I don't know, I'll probably be dead in a few centuries. Not helpful for me, but
probably.
How do we detect the neutrinos to know that it's going to happen then? So what are we using to do that?
So this is kind of, quite a new area in astrophysics. Words that we use or we hear a lot is like multi-messenger astrophysics. So I guess when astrophysics started out, it was all about electromagnetic radiation. So light, so be that X-rays or radios, radio waves. And then we kind of had the era of neutrino detections. And this, I guess they set all these detectors up in the hope that they would see some neutrinos, which eventually they did. So that was from supernova 1987A. They detected a handful, and they were able to say, yeah, that was from the supernova and nearby, galactic pal, the Large Magellanic Cloud. And so at this stage, we've had a detection, we've been detecting neutrinos for 30 years. Unfortunately, we haven't seen any more from supernovae, but there are quite a lot of detectors on Earth that are looking for neutrinos and are just waiting for that kind of next supernova. So there's one on the South Pole called Ice Cube, which extends very, very deep down into the ice, 3 kilometers or something, I think, maybe all the way down. Or
just had a look. Wait up.
Steffi's going to Google it.
I'm already Googling. Well, they just had a discovery of neutrinos from the Galactic Center, which is very cool.
It's very cool, yeah. So it's Ice Cube.
Oh, yep. Did you find out how deep it is, Steffi?
between 1450 and 2450 meters.
Yeah,
2.5
deep.
kilometers roughly. Yeah, that's amazing. Very deep.
Yeah.
Very deep.
So it's just like these kind of strings with little hectors kind of spaced, and then they can kind of see if a neutrino passes through, it's going to trigger a lot, so they can kind of work out where it came from. So there's, Ice Cube on the South Pole. There's Super Kamino Kande, which I think is in Japan.
Yep.
And then I believe they're also building one in Lake Baikal.
The deepest lake that there is.
Yeah, exactly. Because you want to, not have too much interference.
So leading on to the next part, what is the most interesting supernova remnant, and why is it the most interesting?
Good question.
I put this question in having heard you talk about your research, but I don't know
true.
if you can talk about it having published it yet or not.
Well, it's been almost 3 years. I've published nothing, so
excluding the ones that you can't talk about.
No, I don't know. I'm happy to talk about it. I think everyone knows it's a little weird. So I guess in terms of my research, the one that perplexes me the most is called 1EO102-7219 point something. It's not a nice name. I just call it 1EO102. And so it's quite a young supernova remnant in the small Magellanic Clouds. It's been observed a lot because it is lucky enough to be the calibration source for the Chandra X-ray telescope. So when they're doing observing, they're constantly going back to this remnant to check that all their stuff's working well. And as it should be. So we have very good observations, and we know its X-ray spectrum very well, very good, not too many uncertainties, stuff like this. And it's definitely from a massive star. So it shows those kind of telltale signs of coming from a massive star in terms of its X-ray spectrum. However, the thing that interests me is that it's very circular. So when you look at it, it's very round. It's kind of like a shell in the X-ray. Yeah, so we expect core collapse to be more asymmetric. And for some reason, this one that is definitely a core collapse is not showing that pattern. And that's something that me and my supervisor are trying to understand why that might be the case. Maybe it's related to the environment that it's in. Maybe it's related to the angle that we're viewing it from, stuff like this. But I guess one way we're maybe hoping to answer this is normally we look at the shape of our remnants using X-ray light, which tells you kind of about the explosion mechanism. But yeah, I am mainly a high energy astrophysicist, but I've been using some radio observations to try to kind of analyze the morphology of supernova remnants in radio waves. This is more likely to tell you about the environment that the remnant is expanding into. And so if we maybe see that there's not this same correlation in radio, maybe it's telling us that the asymmetry comes from the explosion. I don't know. It's something like this. We're hoping to see whether it's more dominated by the environment or it's more dominated by the actual supernova mechanism.
The explosion is sort of circular in the end?
Yeah, maybe. Like maybe it's the explosion is circular and in fact, it's the environment, and most of these stars happen to be in very, very clumpy environments that really makes your remnant asymmetric. And then maybe for this reason, this massive star, maybe it didn't have massive winds. Maybe for some reason, this massive star just managed to form on its own. There wasn't other stars like kind of muddying up the circumstellar medium.
So you're saying it, so instead of blowing out on an odd shape, it's going nice and round like a planetary nebula would then?
Yeah. So I don't know so much about planetary nebulae. I don't know if they're all, because most of the images I've seen appear to be quite round and
pretty round, yeah.
Yeah, there might be clumpier ones. I'm not sure. I haven't seen them. But yeah, this one is very round, but it shouldn't be based on the supernova type that we know from other means. So yeah, it's kind of a perplexing thing to think about.
I have a question which my brain went to when you talked about...
Your brain went to the 5-year-old child brain, didn't it?
No, my brain went to can the radio help you to look at the 3D structure of the supernova remnants?
Oh, sorry, I thought you were looking at the next question. I'm like,
no. I'm considering what is.
Sorry.
That's I'm excited about the next question. Is it possible to get an idea of the 3D shape of supernova remnants, or are we sort of limited to that sort of everything being a 2D sort of plane?
Everything I've encountered has always been like a projection. We're looking at like the 2D plane. I don't know if X-ray can tell you, but like maybe if you were looking at polarization or stuff like this, or if things were like more blue shifted, you had in certain regions. Like
I know that radio can give you sort of like a spectrum and can give you some sort of 3D.
Yeah.
That way, but I don't know that much about radio astronomy. I'm an infrared.
Me neither. Someone like all the data reduction, and then I just took the images, and I was like, into my code.
You need one of the NWA people to tell us. And then my other question was, I have forgotten it. What was it? It was, oh yes. So when you look at the X-ray images, do you tend to see the same sorts of features as you do in the optical or near infrared images, or are there sort of bright spots in many like different places than you might expect from the bright spots in your optical image?
It can be quite different actually. And there are some types of remnants that will show like radio shells, and then they'll show more X-ray towards the center, especially if there's a pulsar and nebula. So something like the crab, that beautiful picture is mainly X-ray dominated. It's kind of a weird blobby structure. Like there's other stuff in there, but a lot of it is it's not X-ray dominated. And then right in the center, you see the kind of weird pulsar wind nebula structure. There's kind of like a weird little vortex. So yeah, it's not always the same. And often this is what happens, like when we're trying to determine if something is a supernova remnant, there's usually a few things we're looking for. So we're looking for either 2 out of 3. So optical, radio, or X-ray. You don't have to see them all. But if we see 2, and there are certain kind of characteristics for each one that we want to satisfy, if we find 2, then we classify it as a remnant.
And one more question on this. Very specific astro questions.
No, that's good. This is good.
So when you see the supernova remnants, are they always extended sources, or are they often sort of, especially when you're getting further away, like the large and small Magellanic Clouds, so they tend to sort of, become very small and sort of hard to resolve?
No, the Magellanic Clouds is not so far. It's only 50, 60 kiloparsecs. So with Chandra, we're seeing them all as extended. They all kind of look like plates. The only case where it might not be is sometimes it's a remnant, but in X-rays it's only showing emission from some like compact source in the center. So a neutron star. And so if we're not seeing like an X-ray shell, then we would just see like a point. But yes, the Magellanic Clouds are perfect because pretty much any remnant you've got there, we will see it as an extended source. And I believe they can even do this up to M31 as well. So
Awesome.
Yeah, so they do studies like I do in the Magellanic Clouds. There are groups that do it for M31. So we can see quite far away. Obviously, when we look at the galactic remnants, they appear to be bigger. We can get better resolution, stuff like this, but they can still be resolved in other galaxies.
That's impressive into M31.
Yeah. Ring, 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 ring. Sonja, they're telling us that they've detected a supernova that just went off. What are you going to do?
Oh.
I've got another message. It's in the galaxy.
It's in the galaxy. I guess the first thing that we want to know is, so they just detected it. Have you detected the neutrinos, or have you seen like electromagnetic emission?
Let's go with neutrinos detected.
Yeah.
I guess the first thing, so we've seen neutrinos, and neutrinos are really good at passing through everything, even probably the galactic center. So seeing neutrinos means there's maybe been a galactic supernova, but if we're very unlucky, it might be on the other side of the galactic center, and then we're kind of through. Maybe we won't be able to see it at all. If not, like every person would be turning their telescope towards the subject. Every telescope on Earth would be looking at this, and pretty much everyone in space. And this actually, it wasn't a galactic remnant, but quite recently we were very lucky, and there was a supernova that occurred in the Pinwheel galaxy, so M101. And this was the closest core collapse supernova in the last 2 decades, something like this. Yeah. So there was another one in that galaxy. It was a Type 1a supernova in 2011. So we've been very lucky with this galaxy. It's really like churning out the supernovae for us. And so we're getting some really close by ones. Basically the same thing happened. Every amateur astronomer was looking at the supernova with their telescopes at night, taking photos. Every small telescope on Earth, every large telescope, every telescope was regularly looking at this supernova occur. So we could see exactly how the light curve changed and how the spectrum changed with time. So it was really exciting.
I saw a lot of photos on my timeline from the astrophotographers
I have
bombarding it,
a bunch of them that I haven't done anything with yet.
Yes, well, send them to me and I'll stack them and process it for you.
No, they're mine for my students. But you can show me how to stack them at some point.
I'll come in and do a session and stack them with the students.
Yeah, actually, that probably would be useful.
That'd probably be a good way to do it.
So let me we've just detected a UV flash. What would that mean for a potential supernova going off?
You're asking me some questions, Steffi.
I told you I did my master's on this.
Yeah, you explain, because I'm not really a supernova person.
So some call collapse supernovae, when the initial sort of shock comes out, they can let out a sort of flash of ultraviolet photons, and then it can take a little bit longer for the rest of the photons to sort of make their way through the supernova, and we tend to see the higher energy ones escaping first, and then goes down to lower and lower energies. And so one of the cool things about this recent supernova is that because it is in such a highly studied galaxy by many people all around the world, we did have actually lots and lots of data points to try and get a signal of this initial flash before it sort of brightens for a few minutes, and then goes down, and then brightens again properly when the actual shock exits the photosphere of the star properly. One of the really cool things I learned about, so when I was in masters, the 2014 supernova in M83 went off, and I was part of CASTRO, the Center of Excellence for All Sky Astrophysics, sort of precursor of Astro 3D now. Had a big team working on type 1a supernovae for looking at dark energy, and so this was a nearby supernova, which was really great because most of the ones that you detect are further away, just because you're getting more galaxies in your images. You know, the further back you go, it's complicated cosmology stuff. So this was a really highly studied telescope. And one of the cool surveys that was going on at the time was the Kepler survey. And Kepler had a really high time cadence, so it was taking new images very, very quickly. And so it was possible to see changes in the supernova on sort of minute timescales, which was really cool at the time.
Very cool. Kepler is for exoplanets mainly, though.
Yes.
But there we go. Telescopes always helping each other. One thing that I think is very cool is we've been using ATLAS, which is the telescope that's looking for incoming asteroids, I believe.
Yes? Yeah.
And you can use it to look at other things too. It's out there looking for asteroids, but there's fabulous science that you can do with these telescopes that were designed for other purposes.
So are there any stars that are close enough to cause damage to us if they went supernova? Are we in the path of any of those?
Well, the sun would be a problem. But we've got
that's a given, yeah, that's a given.
We got some time. Yeah, I'm actually not too sure if there are. I guess there are kind of different scales of what you would consider damage, though. So for my honors research, we were looking for like evidence of just like isotopes, so specific atoms from supernovae. So if there's a supernova within some distance, you might see atoms being deposited on Earth, but that's not really going to be a problem for us in terms of one that, you know, releases enough radiation that we should be worried. I'm actually not too sure. Do you have any thoughts, Steffi?
Nothing is coming to mind.
So it's safe. Awesome.
I think so. I think even Betelgeuse is 600 light years away, which is pretty far for...
Yeah.
I'd be interested to see what Betelgeuse would do to the night sky for us if it went.
It's a sort of relatively popular simulation of it, but it would be around magnitude -8 to -12, which is about full moon levels.
Yeah.
It's a very small area.
Spoil some stuff for a while.
Yeah, but in a cool way.
Final question. Outside of astrophysics and supernova remnants, do you have any hobbies? Anything to take you away from the madness that is science?
Well, Steffi and I have this in common. We're both cat lovers. I'm obsessed with my cats, and we're in a physics cat mum group chat where we just share photos of cats. Yeah. So I have 2 cats. They're the loves of my life, Sashimi and Lucky.
I love the name Sashimi. That's
very
cool.
cute.
Yeah, so cute. And she loves fish as well. It all makes sense. So yeah, I'm very into cats. I guess I also write for Astrobites, which I guess is not necessarily out.
About that.
It's not out of astrophysics, but it's something I really like doing. So I did do English at university. And I also, this is not my first radio rodeo. I was part of A&E Student Media, and I had a couple of radio shows, which was fun. But anyway, so I've always just liked communicating stuff like this, probably more written communication, which is what Astrobites does. So it's a lot of graduate students, mostly people based in the US, and then me based in a very inconvenient time zone where I'm never awake for any of the meetings. Yeah, basically what we do is we take papers that are published on the archive, which is kind of when you write a journal article for some publication, it's the first place you upload it so other people can kind of see the work. So we take papers that are on the archive and then we kind of communicate them to we kind of aim for undergraduate students. And we just try and make them more accessible. So something that's more interesting, it's more like reading, a publication, like an interesting pop sci article or something like, while keeping the science important, not just having clickbaity titles, I guess. So yeah, that's really fun. And it's a great way to learn. So I only started writing for them at the beginning of this year, but I started reading through them a bit more towards the end of last year. And I feel like it's the way that I've learned the most in astrophysics. Like these articles that make it kind of basic, and you can get those like basic concepts about like things that I never worked with. Like there's no one really at Melbourne, or not many people in Australia who study exoplanets. And there are so many people in the US and they're writing these articles about exoplanets. And I've like slowly started to kind of pick up knowledge about that field that I have nothing to do with, or even galaxies I don't work with so much, and I'm learning more about them. So it's really cool.
I did want to write for them when I was newish PhD student, but didn't really have the time. So I'm really glad that there are a few of my friends who have taken on that. And
are they publicly accessible, those? Or are they? Yeah, they are.
Yeah.
Okay.
So it's just called Astrobytes. There's a new paper summary that goes up every day.
Oh, you know what time it's for? It's like we're up to, Steffi, don't you?
Yes, I do.
It is pop quiz time.
Oh no.
I didn't tell you about
quiz.
this. So the topic for your spot quiz, Sonja, so we take the first letter of your name and choose a topic that starts with the first letter of your name. And I went with soap because I've been watching lots of soap making videos on YouTube since I don't do it myself.
But you need to explain the reason why we do this. We do this because you know so much about your topic. We want to show our listeners that just because you know everything about supernova remnants doesn't mean you know everything about everything. Sort of like that humbling, sort of like everyone's the same in the end. We all have our passions.
Well, I hate to break it to you, but I'm actually a soap expert.
We've already had one run-in with Sarah Webb where we did, what did we do? Sea cucumbers.
Sea cucumbers.
And it turned out that she knew everything about sea cucumbers.
Oh my gosh.
Incredible. Yes, I've been watching lots of soap making videos on YouTube because I don't do this craft myself. And if I watch videos about crafts that I do, I get very jealous when people make things that are prettier than what I make. My first question is, which era is the oldest known soap factory from?
Oh, soap factory. Like, you want a century?
Yeah, a century or a time period. Or civilization, whatever you want to go with.
Oh, civilization. All right.
Maybe that's
the Egyptians.
A little bit earlier, actually.
Oh.
So evidence exists for the production of soap-like materials in ancient Babylon around 2800 BC.
Wow, very cool.
I think that's close to the old period, but
someone should have given it to the British back in the Dark Ages.
We'll get to that.
So she's already marked it 0 points.
Sorry.
She's quick. Which medications are common in hand washing soap? So what metals are
what metal?
are common in hand washing soap?
And this is a chemistry metals, not an astro metals.
So it's not carbon. Okay. Wow, that's hard. Maybe like
Well, I still eat bacon because it's carbon everywhere anyway, so I may as well just keep eating my bacon.
Yeah. I'm going to go with aluminium.
Oh, close, actually.
There's two, so you've got another shot for a second one.
Oh, okay. Magnesium.
Oh, also close, but not quite. We were looking for sodium and potassium.
Ah, that actually makes sense. Yeah, I believe there's sodium in salt.
Yeah, the sodium makes sense. The potassium, interesting.
Yeah,
potassium is used for when you've got hard water.
Oh, cool.
So there's no potassium in Melbourne soap then.
Probably not. I enjoyed this question. What sort of oil was commonly used to make soap in the Middle Ages?
Oil in the Middle Ages. Lard.
Okay, so I've got olive oil because soap made from olive oil smelt much better than soap from lard, and there were lots of olive growing regions in the Mediterranean and in the Middle East. So I might give you a bonus point for that because I didn't specify when the Middle Ages were.
Yes. I love getting points on a technicality. Perfect.
The first soaps were made of lard and other animal fats, but vegetable oils were much cleaner, basically. So that's why they swapped. Pretty
Cool.
quickly,
My old man would turn around and say, "Oh, Mediterranean olive oil. Oh, yeah, you can thank the wogs for that." Everything's the Romans. Everything was because of the Romans.
Oh no, this is the Syrians.
Yeah, but he'd still claim it because it's olives. So, olives, Roman, Italian. Hey, next question. How did the Roman...
I was like, have you read it yet?
How did the Romans clean themselves at baths before soap use became common?
Olive oil?
Yeah.
I gave the answer away without realising. They immersed themselves in baths and then smeared their bodies with scented olive oils. They used a metal or reed scraper called a strigil to remove any remaining oil or grime.
Wow.
I think it's actually a pretty good idea. So, because oils are going to dissolve your body oils because like dissolves like.
Also, when you use makeup removers, a lot of them are oil based. Yeah,
much better than messing around with alkali and things like that.
For sure.
My last question: in the name of public health, how long should you wash your hands for to remove bacteria?
30 seconds.
Yeah. The US Centers for Disease Control, or CDC, recommends at least 20 seconds. They do find that
government recommend.
I couldn't find it. I think they just all took the 20 seconds or the happy birthday singing. But there is evidence that using soap does kill off more bacteria than not using soap. But if you've got no other option, then not using soap is still better than not washing your hands. So
for at least 20 seconds. healthdirect.gov.au.
There we go. But it's probably the same source. You did great. You did better than Mark and I did.
Yeah, I got none. I got none out of 5. But I know nothing about Murder, She Wrote. So I don't know many people like me that would watch Murder, She Wrote.
Well, I got one for The Simpsons, so.
Well, I probably only got maybe one because one of them was spoiled, and then one was a technicality, and then one. If I'd said any number bigger than 20, I think you would have given it to me. So.
Yeah, no, a minute we would have been like, it's an order of magnitude thing.
Okay.
They're absolutely allowed, especially when Fred Watson comes up with his own question and gives himself bonus points. Technicalities are fine. That winds it up, yes. Thank you for joining us. That was actually really interesting. I know that a lot of our listeners are going to enjoy listening to this one. They're going to have a blast with it.
Yeah. Everyone loves Supernova Remnants. They're so pretty. They're so nice to look at. So.
Yeah, there are really so few people here in Australia who study them that I'm really glad that we could get you to come and talk about them. Maybe the prettiness doesn't come across on an audio.
We'll just have to look at YouTube compilations.
So look, thank you very much for coming along. It's been great having you. I've actually learnt a bit, so that's really cool. I didn't realise there were that many supernova remnants in the Magellanic Clouds.
There's so many. We're very lucky to have them there.
I do spend a lot of time imaging around Tarantula Nebula, and I see a lot of extra stuff around there, but I never know what any of it is other than the main ones that are catalogued properly. So
yeah. Well, thanks so much for having me as well. I've had a really nice time.
That's all right.
Chatting about space stuff.
Yeah, next time there is a supernova going off in the galaxy, we'll try and get you on the phone.
Thanks for listening and supporting us as we continue to learn on our podcast journey. If you'd like to contribute to the podcast, you can head to www.patreon.com/Spaghettification podcast and support us for as little as 1 can of beer a day. I'd like to give a shout out to Steve from Home Loans Easy, Jess Stout, Paul Milvain and Andy Ladd for their ongoing support of our podcast.